Right now, somewhere in the Caribbean, a ship the length of 4 city blocks is bending. Not breaking, not flexing in some alarming way, just bending. Slowly, constantly, almost imperceptibly, as the ocean pushes up from below in one place and pulls away in another. The passengers on board are eating breakfast, lounging by pools, watching a show in a theater built 17 stories above the waterline. None of them feel it. None of them are supposed to. That invisibility is not luck. It is the result of one of the most demanding structural engineering problems ever solved in peacetime, repeated, refined, and scaled up until the answer became a 250,000-ton floating city that the ocean cannot fold in half, no matter how hard it tries. The obvious explanation is that cruise ships are simply massive, made of thick steel, too big and heavy to fail. That explanation is wrong, and understanding why it's wrong is the only way to understand what is actually keeping you alive on one of those ships. Here is the real problem. A modern cruise ship is not a rigid object sitting on water. It is a beam, a 1,200-foot beam, partially supported and partially unsupported at any given moment, subject to continuous bending forces that change every time a wave passes underneath it. The ocean does not treat the hull as a platform. It treats it as a structural member, and it is constantly trying to break it. Think about what the geometry of a wave actually means for a ship this size. The Icon of the Seas, currently the world's largest cruise ship, is nearly 1,200 feet long. An ocean wave can be anywhere from 400 to 800 feet between crests. That means at any given moment, different sections of the ship's hull are being pushed upward, while other sections are being left unsupported. The ship is not floating evenly, it is bridging, spanning a gap. And bridging at this scale generates enormous forces at the center of the structure. Forces that, if the engineering were wrong by even a margin, would cause the hull to fold at the midpoint like a piece of cardboard held at the ends. The ship isn't fighting the ocean. It is negotiating with it, continuously invisibly in a language made of steel geometry and calculated stress. There are 2 directions that negotiation can go wrong. Naval engineers call them hogging and sagging. And they are worth understanding not as vocabulary, but as physical events happening inside the hull on every voyage. Hogging occurs when a wave crest passes under the middle of the ship. The center of the hull gets pushed upward by buoyancy while the bow and stern, sitting over the troughs, droop downward under their own weight. The keel, the central spine running the length of the ship, goes into compression. The upper decks go into tension. The ship bends upward at the middle like a bridge whose supports have risen. Sagging is the reverse. Wave crests strike the bow and stern simultaneously while the midsection hangs over a trough with no water supporting it. Now the center sags. The keel goes into tension. The upper deck goes into compression. The ship bends downward at the middle like a bridge whose center has lost its support. In rough seas, the ship cycles between these 2 states repeatedly, sometimes many times per minute. Every cycle is a bending load. Every bending load is stress on the hull structure. And here is the first thing the obvious explanation gets wrong. Making the steel thicker does not solve this problem. A hull rigid enough to simply resist all bending would need to be so heavy it could not float. Beyond that, a completely rigid structure in a dynamic ocean environment doesn't actually stay intact. It shatters. Concrete is rigid. You don't build ships out of concrete. The problem is not one of strength as a raw quantity. It is one of structural geometry, material selection, and distributed load management. Thickness is a small part of a very large answer. To understand why this matters in practice, consider what happened to the MOL Comfort. In June 2013, a container ship named the MOL Comfort was crossing the Indian Ocean, traveling from Singapore to Saudi Arabia with over 7,000 containers aboard. The ship was 316 meters long, it was only 5 years old, built at a high-quality yard, operated by a well-established shipping company. On June 17th, in seas that its own structural models indicated it should be able to handle, the hull cracked amidships. The ship broke in half. The stern sank days later. The bow section caught fire and sank weeks after that. All 26 crew members were evacuated safely, but the ship, and its cargo, was a total loss. The investigation by Japan's Class NK Classification Society concluded that the fracture likely initiated at the bottom shell plating in the midship section. The structural margin, the gap between the load the ship could theoretically handle and the load it actually experienced, was not sufficient when multiple stresses combined in ways the models had not fully anticipated. The conditions that day should not have broken that ship. They did anyway. This is not a story about a poorly built ship. It is a story about the nature of structural failure at scale, and why the question in the title of this video is not hypothetical. Ships can and do break in half. They have done so in living memory, under conditions that engineering said were survivable. So what makes a cruise ship different? The first answer is one that most passengers would never guess. The superstructure. Container ships have large open areas across their main decks. Those openings exist so cranes can reach down into the hull to load and unload cargo. That operational requirement creates a structural problem. An open deck is a weakened cross-section. The hull girder, the structural beam formed by the keel at the bottom, the main deck at the top, and the plating on the sides, loses some of its effectiveness wherever the top is interrupted. Container ships have historically been more vulnerable to hogging-related hull girder failure, in part because of this geometry. A cruise ship is built entirely differently. Its superstructure, the stacked decks of cabins, restaurants, pools, and entertainment venues rising above the waterline, extends nearly the full length of the hull. That continuous structure is not just passenger real estate. Every one of those decks participates in carrying longitudinal bending loads. Not equally, decks higher up contribute less than the main hull, but they contribute. The entire vertical stack of the ship is doing structural work. The passengers walking through those corridors are, without knowing it, inside a distributed load-bearing system. There is a wrinkle here that engineers call the stiffness step, and it is one of the more counterintuitive design decisions in cruise ship construction. The superstructure of a cruise ship is deliberately designed to be less stiff than the main hull. When you first hear that, it sounds like a flaw. Why would you intentionally weaken part of the structure? But the reason is a layered trade-off. If the superstructure were as stiff as the main hull, if the two were equally rigid, they would try to bend together as a single unit, creating a hard stress concentration at the boundary between them. That junction becomes a fracture initiator. Beyond that, a stiffer, heavier superstructure raises the ship's center of gravity, which compromises stability in a different and equally serious way. The solution is to let the superstructure be slightly more flexible, allowing it to participate in bending loads gradually rather than creating a sudden structural step where failures can nucleate. This is the kind of decision that does not show up in any passenger-facing description of a ship. It is invisible by design, justified by physics, and managed by naval architects running finite element models across thousands of load cases before a single steel plate is cut. If this kind of machinery, the invisible engineering hidden inside ordinary systems, is the sort of thing you want to keep pulling apart, subscribing is worth your time. This channel is built specifically around that moment when the surface of a system cracks open and the operating logic underneath becomes visible. There is more of that hiding everywhere. The material itself is part of the answer. Modern cruise ship hulls use high-strength steel, grades like AH-36 and DH-36, that are stronger than the mild steel used in earlier ships without being proportionally heavier. The Titanic's hull used low-carbon mild steel that could become brittle in cold water. Modern shipbuilding steel is engineered to maintain toughness across a range of temperatures and loading rates. The goal is not just strength. It is controlled behavior under stress, steel that yields elastically and returns to shape, rather than cracking without warning. That elastic flexibility is not a side effect. It is the point. Large ships in heavy seas physically bend, not by millimeters but by feet, measured across their full length. That deflection is expected, calculated, and built into the design. A ship that could not bend at all would be a ship that fractures instead. The hull is not trying to be a rigid object. It is trying to be a spring, one that absorbs energy, distributes it across the widest possible cross-section, and returns to neutral. The cross-section is where the real structural logic lives. Think of the hull not as a shell, but as a hollow box beam. The keel at the bottom is under the highest stress in a hogging condition. The main deck at the top is under the highest stress in a sagging condition. The strength of the beam against bending is governed by something called the section modulus, how much cross-sectional material exists at those extreme top and bottom positions, and how far from the neutral axis it sits. More material, farther from the center, means more resistance to bending. This is why the hull is not a solid block of steel. It is a carefully shaped geometry that puts material exactly where bending forces demand it most. The double bottom adds another layer. The space between the outer hull and the inner hull is not just a safety feature against flooding, though it is that. It also functions as a structural box in itself, adding depth to the cross-section and increasing the section modulus. Transverse watertight bulkheads running across the ship's width divide the hull into separate compartments. Those bulkheads resist racking, the tendency of the hull cross-section to distort sideways and distribute loads across multiple structural paths rather than concentrating them in a single critical member. The ship is built in modular blocks. Steel sections are fabricated separately, sometimes at different shipyards across different countries, then assembled and welded together. The Icon of the Seas required roughly 2,600 workers from more than 20 countries over several years just to assemble the physical structure. The structural engineering work, the modeling of every deck's contribution to bending stiffness, the analysis of every load case the ship might experience across a 20-year operational life, the calculation of how hogging and sagging interact with wave-induced torsion and dynamic impact loading, that work took place years before the first steel was cut. The ship you see in a harbor photograph is the final answer to a mathematical problem that took longer to solve than the physical construction took to complete. Which brings everything back to where this started. Right now, on a ship somewhere in the Caribbean, the ocean is passing underneath the hull in long, slow swells. The midsection of the hull is rising slightly. The bow and stern are dropping slightly. The keel is under compression. The upper decks are in tension. The structure is bending, by design, within calculated limits, returning to neutral before the next wave arrives. The passengers feel nothing. They have no reason to. The entire purpose of everything described in the last several minutes is that they never would. The MOL comfort broke in half because its structural margin was insufficient for the combination of stresses it encountered. Cruise ships carry inherent structural advantages that container ships have historically lacked: continuous superstructures, greater cross-sectional depth, multi-layer redundancy, and decades of design refinement built on exactly that kind of failure. Not immune, not invincible, but engineered across every layer of the structure to stay intact under the forces that an ocean generates against a 1,200-foot beam every hour of every voyage. When you walk onto a cruise ship, what you see is a resort. Pools, restaurants, theaters, cabins with balconies, a water park somewhere on the upper decks. What you are actually standing inside is a structural system designed to negotiate continuously with the ocean without ever letting you know that negotiation is happening. The comfort is real. The invisibility of the system producing it is the achievement. And the bend you never feel is the whole thing working exactly as intended. I hope you enjoyed the video and learned something new about one of the most fascinating engineering marvels ever built by mankind. If you want more content like this, please subscribe and hit that like button. I'm Larry, and this is the Ship Files. Thanks for watching, and I'll see you in the next one.